So to date, we have been concerned with explicitly defined functions. Explicitly defined functions are ones where you give me an x, and I have an exact expression for how to find y. Right? So, exact expressions. So explicit expressions are ones that are exact. Here's exactly what y is. You give me an x, here is what y will be. That might be contrasted with implicit functions. Functions where, I'm using functions loosely here, but relationships where the relation between x and y is implied by the expression, right? You could give me an x, but I'm going to have to solve an equation. I'm going to have to futz with this equation in order to come up with what y might be, right? X and y are all kind of tangled up in implicit expressions, right? These are implied relationships. Implied relations. Anybody know what this looks like if you were to graph it? X squared plus y squared equals 25. It's something we should have seen before now. It's a circle of radius 5. You will notice that it is not a function. Right? It fails the vertical line test. But, right, it is this relationship between x and y, and we still might have the same types of questions. Questions like, at this point, what is the slope of the tangent line? Right? How fast is y changing as x changes at this specific value? It may just be that at that specific value, you need both an x coordinate and a y coordinate. If you tell me x is 3, I need to know whether you're talking about this point when y is 4, or this point down here when y is negative 4. Right? So just an x value won't be enough. But it's the same type of thing that we're asking. So if I wanted to differentiate a function that looked kind of like this, what would I do? Well, one thing that I could do is just try to turn it into an explicit function. So I could try to solve for y. Y squared equals 25 minus x squared. So y is plus or minus the square root of 25 minus x squared. That's really two different functions, right? This is y equals the square root of 25 minus x squared, or y is the square root of 25 minus x squared, and it's the negative square root. That's two different functions. One of these is the top half of the circle, and the other one is the bottom half of the circle. So that's one thing I could do. I could say, oh, well, I'm interested in this point. It's in the top half of the circle. So let me talk about this function that's explicitly defined, and I can find the derivative of this guy. That seems like a lot of work, but it seems like work I can do until I get to maybe a different kind of problem. Now I've got x's and y's all tangled up, and I'm going to have not a fun time trying to solve this for y. A very not fun time. Okay, so what are we going to do? We're going to treat y as a function of x. we're going to say that what y is really is this kind of complicated relationship that I'm too busy to find. So when I see something like x squared plus y squared equals 25, I'm really thinking this is x squared plus some mystery function squared equals 25. If you gave me an x, I could tell you what this y was. But I'm not going to take my time to figure out exactly what it is here. And I'm going to run through both sides of this equation with a derivative. I want to find how is this function, how are these expressions changing as x changes? If x squared plus y squared is always 25, then the rate at which this side is changing should be the same as the rate at which this side is changing. I'm adding these together. I know what the derivative of x squared is with respect to x. What's the derivative of x squared? 2x. What's the derivative of y squared? Not exactly, but it's pretty close. Y isn't really y, right? Y is, it's a whole function. This is a bunch of stuff, right? And this y doesn't match up with this x that I'm taking the derivative with respect to. What this really is a bunch of things squared. So the derivative should be 2 times that function raised to the first, and then what? Absolutely. Times that thing's derivative, using the chain rule. Okay? So times whatever that thing's derivative is. We can call it y prime, or you can call it dy dx. I don't care which one you use. I usually stick to dy dx because I think it is a little bit more exact than y prime. I don't know whether this tick mark is a first power, or it's really easy to lose a tick mark when you're looking at an entire expression. And dy dx stands out a whole lot. So that's why I use this dy dx. But y prime is a lot easier to write. So just do it however you want to do it. Right? What I've really done here is I've used the chain rule in order to differentiate y squared. I want to know, how is this thing changing as x changes? Well, y isn't an x. So I'm going to treat y like it's a big complicated mess in terms of x, and take its derivative. So the power comes down, the inside stays the same. Right? The power comes down, the inside stays the same. I reduce the power by 1. But then I have to multiply by the derivative of that thing using the chain rule. And then what's the derivative of 25? That's 0. Right? So what I really have here is 2x plus 2y dy dx is equal to 0. And this is what I want, right? This is what I'm after. I'm interested in dy dx. So let's solve for it. Let's try to get it alone. I'm adding 2x, so let's subtract 2x. I'm multiplying by 2y, so let's divide by 2y. So now I'm left with just dy dx on the left side, and on the right side I've got negative x over y. So there's the derivative. Notice that it depends on both an x value and a y value. Remember that this was a circle, and I'm expecting that, right? If I want to know what the derivative is, if I want to know what the slope of this curve is, I've got to tell you an x coordinate, and I'm probably going to have to tell you a y coordinate too, because there might be multiple y's that correspond with it. Yes?
When you did the derivative of like the x thing,
Uh-huh.
is that the 2y?
Yeah, that's
derivative?
f of x and y are the same thing.
Okay.
Right? So the y is a little bit easier to talk about than the big f of x, but the derivative of this would be 2 f of x to the first f prime of x. So I'm going to treat this as 2y to the first times its derivative. The general rule of thumb here, you might write, right? You're taking a derivative of whatever these things are. I want to know if the variables match. If they do match, then I can just take a derivative like I normally do. The derivative of x squared is 2x. If they don't match, right, if I'm looking at the derivative with respect to x of y, or of t, or of z, then I'm going to have to use the chain rule, right? I'm taking the derivative with respect to x of y squared, so the derivative is going to be 2y dy dx. I've got to have this last bit, the bit that I'm using the chain rule on. Because I'm treating y like it's this big complicated function in x's instead of just a regular old y. So let's see that other example. X cubed plus y cubed equals 6xy. And let's do this. Find dy dx at the point 3, 3. So I'm looking for the slope of this curve at a specific value, 3, 3. Notice that if I plug 3 in for x's and y's, this will be a true statement. So 3, 3 is definitely on the curve. It is one of many values that are on the curve. 3 cubed is 27, so 27 plus 27 is 54. And then 6 times 3 times 3 is 6 times 9, which is also 54. So that's a point on the curve. 0, 0 is another point on the curve. 0 cubed plus 0 cubed is the same thing as 6 times 0 times 0. So there are a bunch of points that are on this line. I'm interested in what the slope of this curve is at this particular point. So let's take derivatives. What's the derivative of x cubed plus y cubed going to look like?
3x squared plus 3y squared times dy.
Absolutely. Right? X cubed, I'm taking the derivative with respect to x. So the derivative of x cubed is 3x squared. The derivative of y cubed is going to be 3y squared dy dx, because y is not an x, and I'm taking a derivative with respect to x. This dy dx exists because of the chain rule. Right? What about taking the derivative of 6xy? It is not just 6. It will not be 6 dy dx. I've got a little bit of a problem here. My problem is that I have x times y.
36.
I'm treating y like an entire function. So this is x times this complicated thing. And if I want to take the derivative of x times something, or 6x times something, I will have to use, because this is a multiplication problem, I have 6x times y, and I want to take the derivative of this multiplication problem. I've got to use the product rule, right? This is a product over here. Right? So, right, it'll be 6, the derivative of 6x, times y just left alone, plus 6x just left alone, and then the derivative of y. And what's the derivative of y? 1 dy dx. Because 1 doesn't match, y doesn't match x. So it's going to be 1 dy dx. All right, so here's the whole thing laid out. I have 3x squared plus 3y squared dy dx equals 6y plus 6x dy dx. I have two options from here. One option is to find out what dy dx is exactly. So I need to solve this for dy dx. I'm interested in what dy dx is. I better get that by itself. So let me get all the dy dx's together. This 3y squared dy dx has a dy dx in it. It's got a y prime in it, so I'm going to leave it on the left side. This term, 6x dy dx, it has a y prime in it. So I'm going to move it to the other side of the equation. So I'm going to subtract 6x dy dx. And then all the stuff that doesn't have a y prime in it, I'm going to move it to the other side of the equation. So there's going to be a 6y over here on the right. It was already there. And this 3x squared on the left, it doesn't have any y primes in it. So I'm going to move it to the right side also. So minus 3x squared. So notice I've got all the dy dx stuff together, and then all the not dy dx stuff together. And then everything has a y prime in it, so I can factor that out. And now I have dy dx times this thing equals 6y minus 3x squared. I want to get rid of this thing, but I'm just multiplying it by dy dx. So if I want to get rid of it, I'll divide. So dy dx is 6y minus 3x squared divided by 3y squared minus 6x. Ta-da, there's dy dx. Is that what I wanted? What am I looking for here? Find dy dx at the point 3, 3. Am I done? Yeah. I'm just going to plug in 3, 3. So writing this in Leibniz notation is painful. Right? Here's the derivative dy dx evaluated at the point where xy is equal to 3, 3. This is why Leibniz notation is painful, but this is the way that it might be written. And then I just have to plug and chug here. I'll just plug 3's in. So 6 times y is really 3, minus 3 times 3 squared, x is really 3 also, over 3 times 3 squared minus 6 times 3. That's 18 minus 27 divided by 27 minus 18. It's going to be negative 1. Oh, there we are, negative 1. Yes?
I get all the steps you took, except could you run back to when you took the derivative of 6xy, you just say those steps again?
Yeah.
Did that derivative.
So this is going to be an issue, I think, in general, right? That I need to recognize that I'm multiplying two different functions here together. Right? I'm multiplying 6x by y. Y is a big, complicated function in terms of x that I don't know what it is. So I'm going to use the product rule, and let me just do that here on some blank space as an aside. And I'll do it in Leibniz notation. Okay. So I'm taking the derivative of 6x times y. So that's the derivative of 6x, okay, the derivative of the first factor. I'm going to leave the second factor alone. Plus, I'm going to leave the first factor alone, and I'm going to take the derivative of that second factor, the derivative of y here. The derivative of 6x, the x's match up. So the derivative of 6x is just 6. This y is not being differentiated, so it's just y. And then 6x is not being differentiated, so it's still 6x. But this y is being differentiated, and it's being differentiated with respect to x, which is not its own variable. So I'm going to take its derivative normally, which is just 1, but then I have to multiply by its derivative with respect to x. So this is 1 dy dx, 1 y prime. I've got to multiply by that y prime after using the chain rule.
So in that far right parentheses, that y, the 1 is because you took the derivative of y.
Right.
Its derivative is 1, but you did essentially the chain rule.
Yeah, and then I use the chain rule to take the derivative of y with respect to x after. So if the variables do not match, you've got to use the chain rule. You're going to wind up with a prime at the end of it. Questions about this in general? Anybody want to see this done a little bit easier? A little bit easier? Moderately easier? So we had this, and we found that the derivative was this. So 3x squared plus 3y squared, y prime, equals 6y plus 6x, y prime. I'm going to use the y primes instead of the dy dx's here. Okay? So we already did this step, right? I just took the derivative. And I want to know, find y prime at 3, 3. Well, why solve for y prime in terms of x's and y's if all I'm going to do is evaluate it after? Why don't I just evaluate it now, and I can talk about a bunch of numbers instead of talking about variables? So I know that x is 3 and y is 3, so this is really just 27 plus 3 times 9 is 27, y prime equals 6 times 3 is 18, plus 6 times 3 is 18, 18 y prime. And now I have an equation that's all numbers and y primes instead of too many variables. I just need to solve for y prime. Move all the y primes to one side. 27 y prime minus 18 y prime is 9 y prime. And if I subtract 27 from the right side, I get negative 9, which means that y prime is negative 1. Yay. It's a little bit easier. So if I want to evaluate these derivatives at specific points, your best bet is to differentiate, but then don't solve for anything. Don't move stuff around until after you've plugged in the numbers. Now, if I ask you to find y prime explicitly, if I say, find y prime, here's an equation. Well, then I need to know something general, something like 6y minus 3x squared over 3y squared minus 6x. Here's what y prime is in general. So if I want to know what's the derivative when x is 1 and y is something else, or when y is 0 and x is 0, I can see that, oh, well, that derivative won't exist because I'll get 0 divided by 0. This function actually looks like this. Here's kind of the general shape of it. Kind of like this. And 3, 3 is a point that's kind of out here on the edge. Right? Its slope is negative 1. And so you can see here at 0, the derivative from the different directions, it's not going to exist. It's kind of a vertical tangent. Or you could think of it as a flat tangent. It's two kind of different tangent lines. It's not an agreement. So there won't be a derivative there. But if I were to come up with some other point, right? What's the derivative out here? Well, if I knew the exact function, I could just plug in the x value, plug in the y value, and have at it. So that's the advantage of having the whole function. But if I don't care about every point, if I'm only interested in one point, why solve it in general? I'll just plug the numbers in early, and then I don't have to do as nasty of an algebra job. So this is helpful. Questions about this at all? This process where we're kind of using the chain rule to evaluate these derivatives, it's called implicit differentiation. We're finding the derivatives implicitly. Right? Because we're going to take the derivative kind of normally and then find out what y prime is after that, but we still have these y's that are kind of in there. It's difficult for us to find explicit expressions that involve y prime, but it's a valuable tool, implicit differentiation. Questions? So, implicit differentiation. There are a lot of things that have like kind of non-functional paths. Right? Say, for instance, the Earth's path around the sun is elliptical. Right? So if you drew an ellipse, it's kind of an oval shaped. It's not a function, but we might be interested in kind of the trajectory at any point, right? Given a particular orientation of space on a disk. Right? What's the slope there? I don't know, that kind of thing. Questions? No? All right. So let's talk about another thing that implicit differentiation is going to help us to do.